I then moved to Scotland. Martin came here, so that makes me even meaner than, well, Martin's not mean, but I used to joke I'm the meanest man in the UK. Probably still true. I'm also one of the laziest, so I want to calculate the whole of this matrix in order one operation per entry. So it's got order enter 2D things. I want to calculate each entry with order 1 operation. Of course, that's not going to be reasonable. If you say I want the 6-5 entry calculate in order 1 operation, I'm not going to be able to do it. But if you say you want them all, it's reasonable for me to ask whether I can give you them all at a cost of order 1 operation per entry. That would be the optimal complexity to generate the mass matrix. You're not going to do any better than that. And this has been a question that's been floating around for a while, because already this is the leading term in the complexity. It's easy to find algorithms where the complexity is order n to the 4D, and some people are actually doing that. That is just killing me. So I'd like to do it in optimal complexity. So I told this to, we worked out what the cost was if you do the technology that you find in the book by Karniadakis and Sherwin, Duffy transformations and so on. And their complexity is order n to 2D plus 1. That was actually news to Spencer when I told him about that. But anyway, that's not too bad. They're almost there. But it's not optimal. You know, I mean, if I want to go to order 1,000, if I want to compete with the spectral people, that one there is going to be important. So I'd like to be optimal. There is a paper by Eibner and Melink where they figure out how to do it. But the way they do it is they add extra basis functions. So they had in 3 dimensions, they had 6 times as many basis functions. And this is a great idea. You add more basis functions. You don't add these basis functions to improve your approximation. You add them so you've got more degrees